estime vraiment une bonne majeure avec des inégalités de Fourier inverses pour les vraiment des fonctions harmoniques. Ah oui, donc on essaie de montrer ça sur les. C'est sur des boules. Il faut que le problème, c'est que tu as des boules qui rencontrent des singuliers. Et,
You may start whenever you wish.
Oh, great, thanks. Well, thank you for coming back. So I'm just going to start where I finished last time. So this was formerly still lecture 1C, and I focused on this resolution of Perelman's conjecture question, that there's some reasonable definition of a weak Ricci flow through singularities, and that we have existence and uniqueness within this class. Okay? And so in order to somehow, so what I want to do in the next few slides is explain to you what this flow is and how it is constructed. And then later formulate the main uniqueness result. Okay, so just to recall, previously we were looking at this Ricci flow with surgery, which was given by a sequence of Ricci flows. And the Ricci flows, they were related by these transition maps, which were isometries. Okay, so these transition maps were just isometries between the two time slices minus the surgery points. And so surgery points are just points that are either removed or added during the surgery process. Okay, so all I'm saying is we're not changing the metric away from that. And so what I want to do now is I just want to take this flow and I just want to slightly change the way we're thinking about this flow. So instead of talking about the sequence of Ricci flows on certain manifolds, I want to think of somehow the flow as some kind of space-time, right? So what I'm going to do is I'm going to take the Cartesian product of each of these Ricci flows, so M1 cross the first interval and so on. And so these will be some kind of space-time slabs. And then I'm going to use the transition maps phi to glue together these different products, Cartesian products. Okay? And so you'll see that we'll have something awkward happening near these surgery points. We basically have these two different, like this kind of, if we glue together these two time slices, we have this kind of forking behavior. And so just so we don't have to worry about what happens near surgery points, what we're going to do too is we're going to remove all surgery points. So all points that are added or removed or in a surgery process within that one time slice, we're going to remove those. Okay? Okay, so this is what we're going to end up with. So we have these products, and we're going to glue them together, and then we're minusing a set S, and S is just M1 cross T1 minus U1 minus, and then M2 cross T1 minus U plus, and so on for every other time slice, okay? So the way that I like to draw this is like this. I would like to draw this as some kind of four manifold, space-time four manifold. And then at every surgery time, we have this kind of hole, right? Maybe I shouldn't put a question mark. It's just, there's just some incompleteness because we've removed the surgery points. So that this object is really a manifold. All right. And so this object comes with some additional data. So it comes with a time function, which is just the corresponding projection onto these intervals. Then time slices are just going to be the level sets of the time function. So they're just going to be subsets of space-time manifold. Then we also have a time vector field, which also just corresponds to the standard vector field on these intervals. And observe that if we take the derivative of the time function and the time derivative in the time vector field, we always get 1. And then the metric, the Ricci flow metric, will now induce a metric on the horizontal distribution within the tangent space of the space-time manifolds. Okay, so this is the distribution which is tangent to the time slices. Okay, and we're going to choose the Ricci flow gives us a metric on this. Okay, so we don't have a Riemannian metric on the space-time. We just have some kind of sub-Riemannian metric. Okay, just tangent to the time slices. But we can still compute the Ricci curvature just by computing the Ricci curvature in every time slice, and then we can write down the Ricci flow equation similarly as before, but now we have a Lie derivative term on the left-hand side. All right. So whenever I see objects of this form, I will call these objects Ricci flow spacetime. Okay? So these four objects, and often I'll just abbreviate this Ricci flow spacetime by M and omit the other three objects. Okay? And again, I just want to recall here that in this construction, we have removed points here, so certain time slices are incomplete. More or less they're kind of holes of scale delta. Delta was the surgery scale, okay? in this flow. Okay. Okay. Let's recap. So what are the properties of the spacetime? So there are two interesting properties. So first of all, this spacetime satisfies the epsilon canonical neighborhood assumption at certain scales. So let's just recall what this was. So the epsilon canonical neighborhood assumption said that at points of certain scales, these are locally epsilon modeled on final time slices of kappa solutions. And for a spacetime, I can still make sense of this condition. I can just look at every single time slice and ask, so these are Riemannian manifold, and I can ask whether high curvature points are epsilon modeled on kappa solutions. And recall that the condition of epsilon canonical neighborhood assumption just concerns time slices. And it satisfies the epsilon canonical neighborhood assumption at scales between some constant c delta and some r, which may depend on epsilon. Okay, so as long as the scale is small enough, i.e. the curvature is large enough, and as long as we're somehow sufficiently above the surgery scale. Okay? Okay? So this is somehow normal for the canonical neighborhood assumption. We just need to be at almost singular scales. And this lower bound on the scales I've introduced to avoid that we're somehow near one of these surgeries here. Okay, so I don't want to pick points near these holes because we won't have a sufficiently large ball near these holes compactly contained in the time slice. Okay, and so we have this epsilon canonical neighborhood assumption, and then also this flow is C delta complete. So what does that mean? I call a flow R not complete if the following is true. Maybe I should say briefly, C delta complete basically means we have holes of size no bigger than delta or some C delta in this flow. Okay, okay, so how do I make this concrete? I call a Ricci flow, a Ricci flow space-time, I call it R not complete, if the following is true. Whenever I take a curve defined on a half-open interval, a smooth curve, that satisfies one of the following conditions. So either it's a curve that's fully contained in a single time slice and its length is finite, or the curve is a trajectory of plus or minus the time vector field. Okay, so it's basically either horizontal or vertical. Then whenever the infimum of the curvature scale is bigger than R naught, strictly bigger than R naught, then the limit exists. Okay? So in other words, if we're walking horizontally, finite distance, or vertically, then we can only run out of the space-time if the curvature scale goes to R naught, or goes to or below R naught. So this is some kind of completeness, as in the Riemannian case. Okay. So another way of saying this, and in the compact case, this would be equivalent, would be to say that if we look at the super level sets of rho of these curvature scale, so remember that's the scalar curvature to the -1/2, and then we restrict the times, then these subsets within the space-time are compact for any R prime bigger than R naught. Okay, so if we're just staying away from these holes, we have compact subsets. Are there any questions on this? Oh, I should also say I posted the lecture notes on the chat in the chat function on Zoom. Okay, so to recap, we first constructed a Ricci flow with surgery, and then we just converted this Ricci flow with surgery into a space-time that had these two conditions. Okay, so I haven't done very much. I've just changed from one picture to the other. I could also go backwards if that was necessary. But some of the advantage of thinking about the space-time picture is now that I can take limits. Okay? So this is some kind of manifold and I can take limits. And in the limiting process, the number of surgery times, or the number of these singular times, could accumulate potentially. So I don't have to worry about things like that. Okay, so now if, and in fact, this is possible. Let me see. So what Kleiner and Watt did in 2014 is that they proved a compactness theorem for Ricci flow spacetime. So there's a good sense of convergence of Ricci flow spacetimes, similar to Cheeger-Gromov convergence, and they basically proved the corresponding theorem to Cheeger-Gromov compactness for Ricci flow spacetimes. And then they did the following. They said, well, given some fixed initial condition, let's construct Ricci flow spacetimes, or so let's first construct Ricci flows with surgery for smaller and smaller delta I. Then this generates a sequence of Ricci flow spacetimes, which is just peek on the previous slide, satisfy the epsilon canonical neighborhood assumption. And all that changes is the lower bound. This delta I goes to 0. And here also the delta I goes to 0. Okay. And then in the limit, and then we may pass to a subsequence, and in the limit we get some nicer, hopefully nicer Ricci flow spacetime that I tried to draw here. Okay, so this Ricci flow spacetime doesn't have these holes of size delta anymore because delta is going to 0. Okay? And so this limit is what they call a weak or a singular Ricci flow. So I'll refer to it as a singular Ricci flow starting from this initial condition. Okay? So what's the definition of a singular Ricci flow? So it's surprisingly simple. It's just a Ricci flow spacetime that is 0 complete, okay? Meaning that the surgery scale is effectively 0, and that satisfies the canonical neighborhood assumption below some scale or epsilon. Okay, so what has changed from the previous slide is just that we set the delta to 0, okay? And we can do this now. Maybe just a word on this 0 completeness. Maybe I'll just show you the previous slide. So this definition has been designed in such a way that it also makes sense for R naught being equal to 0, because then it still somehow says something, because it says that the infimum, if the infimum is positive, then the limit would exist. Okay? So meaning we can only run out of the space-time if the curvature scale goes to 0 or if the curvature goes to infinity. Okay, so how should we imagine a singular Ricci flow? So, well, I try to draw approximately what a singular Ricci flow should look like. So first of all, if we start with some initial condition, it basically looks like a normal Ricci flow or the corresponding space-time of it. And then we may see this neck pinch, and we'll just see that in this singular Ricci flow, the neck pinch will just really shrink down to some kind of, singular neck pinch. Topologically, some double cone minus the vertex. And then for any time that's bigger than that singular time, this double cone is being resolved by these two bowls, okay? So there's no discrete step anymore where we perform a surgery. It just immediately resolves out of the singularity. Okay. So now if we somehow combine these two conditions, zero completeness and epsilon canonical neighborhood assumption, well, then this basically tells us that the only way we can get to the singular point, well, is by following curves where the curvature increase goes to infinity. But then at some point, the canonical neighborhood assumption kicks in. So if we want to reach this singular point here, for example, or this virtual singular point, then at some point near this singular point, we have to satisfy the epsilon canonical neighborhood assumption. So that means near these singular points, we always need to look neck-like or Bryan-Soliton-like and so on, right? Or spherical for these extinct singularities. Okay? So this is approximately how we should think of this flow, and this is very similar to the level set flow or the Brachio flow as well. Okay, let me just make a few remarks though, because there's some cause for misunderstanding here. So first of all, the name may be slightly misleading. So we call this a singular Ricci flow, but recall all the objects that we're dealing with are smooth everywhere. Right? So a Ricci flow spacetime is defined as a smooth manifold, equipped with a smooth metric and a smooth function and a smooth time vector field. Okay? And so the reason for this discrepancy is that we're essentially thinking of the singular Ricci flow as some other object, and what we're talking about is just the regular part. Okay, so essentially, this Ricci flow spacetime is the singular Ricci flow minus all the singular points. So if you want to get somehow the true singular flow, what you could do is you could take the metric completions of every time slice, and that would just amount to adding a discrete set of points to every time slice. But it doesn't seem to be very useful to talk about the singular flow. It's mostly useful to talk about just what happens on the regular part of this flow. Okay? And so this approach is different from the mean curvature flow approach, where in mean curvature flow, we can actually really make sense of the mean curvature flow equation on the singular points. Okay, and so here, it's just not, we don't see a very good way of making sense of the Ricci flow equation in the singular setting. So that's why we're not even talking about the singular points. And instead of saying what the flow does at the singular points, we just say what the asymptotics are near the singular points. So that near the singular points, we should look neck-like or spherical. And moreover, this picture might also be a bit more complicated because we may also have accumulation of singular time. So I tried to draw this here, where we may see some singularity that's resolving, but immediately going back to a singularity, and we could have some kind of Cantor set of singular times. Right? So the only thing that we know, and I should have added this here, is a result due to Kleiner et al. That states that the set of singular times in such a flow must have Hausdorff dimension no bigger than 1/2. Okay, so the set of singular times is definitely a set of measure 0, but we don't know if there's any accumulation. We just don't know any example in, or we don't know proof that can't happen. All right, are there any questions on this? All right, so this seems like a much more canonical flow because it doesn't look like we have to make any choices. But here's a word of caution. well, this flow was obtained using a compactness theorem, okay? So within the construction, what we had to do is we had to construct a sequence of Ricci flows with surgery. And we had many choices to do this. And then we had to choose a subsequence of this sequence that converges to our singular flow. Okay? And so if you had to choose a subsequence, maybe we could just choose another subsequence, which maybe gives us another limit. Okay, so so we have existence of this flow, but we definitely don't have uniqueness. So in other words, what could happen is that maybe there are different ways that the singularity could resolve. Okay, or if we have accumulation of singular times, it could be even more messy. Okay, so this was open after Kleiner and Lott's work, and then this was finally resolved in our theorem with Bruce Kleiner, and this is the theorem that I want to talk about in the following. Okay, so more specifically, what we show is the following: we show that there is a constant epsilon can, it's some universal constant, such that the following is true: every Ricci flow spacetime is uniquely determined, of course, only up to isometry, by its initial time slice, provided that it is zero complete and satisfies the epsilon canonical neighborhood assumption below some positive scale. Okay? So in other words, if we take two singular Ricci flows with isometric initial data, and if they both satisfy these two conditions, then they have to be isometric, or somehow the isometry extends over the entire flow. The isometry at time zero extends over the entire flow. Okay. Okay. And I'll talk a little bit more about this result later. So this, somehow this specific advantages of this result later. So for example, we don't really need any compactness condition here. We could even start from some singular data. And maybe just one nice application here is that the result shows us that in our definition of singular Ricci flows, it's actually really enough to focus on one single epsilon can. Okay? So recall in the definition of a singular Ricci flow, we said that we satisfy the epsilon canonical neighborhood assumption for any epsilon below some scale. But we already have uniqueness if this is true for some, or if this is true for some small epsilon can. Okay? And so therefore, the flow would already be uniquely determined. And since there is a flow that satisfies the epsilon canonical neighborhood assumption for every epsilon, this would give us that we can reduce our definition to this epsilon can. And then, of course, let me just restate this main reason why we care about the uniqueness theorem is because if we put together the existence and the uniqueness, then we get that for every compact Riemannian manifold, there is a unique canonical singular Ricci flow spacetime with this manifold as its initial condition. Okay? So this should answer Perelman's conjecture. Okay, so there's one further aspect of this theory that I just want to give you a brief idea, and we'll discuss this later. And the byproduct of this uniqueness theorem is a continuity statement of Ricci flows. And here, for now, I just want to give you an intuition what I mean by this. Okay, so let me take a continuous family of Riemannian metrics on a given manifold. So they don't have to, they shouldn't evolve by the Ricci flow or anything. It's just some continuous family of Riemannian metrics. And now what I want to understand is I want to understand the corresponding canonical Ricci flows starting from these metrics. And I want to understand how they behave if I change the parameter s. So s runs from 0 to 1. So let me make an example here. So I'm going to start with some rotationally symmetric metrics just for simplicity. And they should look like some, these dumbbells where the neck here is very wide and the neck here is very thin. So s goes from here to here. So this should be 0 and this should be 1. And this is 1/2, let's say. So now for every s, I can evolve these metrics by this canonical singular Ricci flow. Okay, so maybe here I just get a standard round singularity. And here I may get a neck pinch. And so now I can ask, well, how do these flows behave if I move the parameter s from here to the right or from here to the left? Well, here the singular Ricci flow is just the same. It's just given by a conventional Ricci flow on a single manifold. And just by standard parabolic theory, what we get is that if we change the initial condition continuously, then the flow will change continuously with it. Okay? So if we move S over to the right, then this flow will change continuously up until we hit some flow that may develop some singularity. So maybe we see some cap singularity here, and then the flow will be continuous up, but not including to this parameter. But it will still extend continuously up until that first singular time. Okay? So here we're still continuous up until this time. And then similarly, we could do this on the right-hand side. We could say, well, if we change the initial condition, then at least up until the first singular time, the flow should change continuously with it. And then maybe there's some way of extending these flows in such a way that they pass the first singular time, such that they depend continuously on S. But the question is now, what happens when we hit this critical parameter? So we could hit it, we could somehow view this critical flow here as a limit of conventional flows from the left, or we could view it as a limit of these neck pinches from the right. And there could potentially be two different limits. But uniqueness tells us that there can only be one such flow, and therefore the two limits have to be the same. Okay? And so this should at least suggest somehow that uniqueness has something to do with continuity. Okay, so this will tell us that these flows really depend continuously on S. Okay? And so this is the further result that we get from this, and I'll have to make this more concrete later. Okay, so it states that every continuous family of Riemannian metrics on a compact manifold gives rise to a continuous family of Ricci flow spacetimes. And again, I have to say more precisely what a continuous family of Ricci flow spacetimes is. All right. Okay, so let me just show the final slide here. Again, this is the theorem that I want to focus on, this uniqueness theorem. And I'll just give you a brief outline of the structure of the proof. So what we'll have to do first is we'll have to discuss the blow-up analysis of the singular part. So we've done this in most parts in the first lecture. We'll do a little bit more today about this. We'll discuss this a bit more. And then what lies at the heart of this uniqueness theorem will be a linear stability theory, local stability theory. And then there will be a slightly more technical construction of a comparison map and a spatial extension principle, which I'll hope to cover tomorrow. All right, so now let me move on to the official second lecture. So what I want to do in this lecture is I want to focus on the proof of this uniqueness theorem. So this is the first part of this proof. And it'll be structured as follows. So first, I'll just say a few, I'll somehow coin this terminology of strong epsilon necks. So this shouldn't take us too long. And then I'll set up a toy case. I'll set up a case that we want to consider for just to understand this uniqueness proof. So this will be somehow an interesting enough case. Then I'll also want to briefly discuss uniqueness in the non-singular case, so we can draw some of the main ideas from this. And I'll discuss the local stability analysis. Okay, so let me discuss strong epsilon necks. So this is going to be just a definition and a little bit intuition, because I'm going to use this terminology quite often in the following. Okay, so recall again, we defined the curvature scale as 1/3 of the scalar curvature to the -1/2. And one particular important class of singularity models was the cylinder. And so what I'm going to do now is I'm going to write down the cylinder in the round shrinking cylinder, so which is on this 2 cross R, in such a way that, with some time shift, and I've chosen the time shift in such a way that at time 0, the curvature scale is equal to 1, and at time -1, the curvature scale is equal to -1. Okay? And so that's the only reason why I've chosen this 1/3 here. I just want to have nicer numbers here. Okay, so just to recall, if we start with a cylinder of curvature scale 2 and we wait for 1 second, then it has curvature scale 1. And I could choose different numbers, it would work the same way, but I just like having these two numbers. Okay, so now let's consider a Riemannian manifold. Then I want to say what an epsilon neck is. So an epsilon neck is defined to be an open subset of M, such that there is a diffeomorphism from a piece of a cylinder, so S2 cross some large interval, minus 1 over epsilon to 1 over epsilon onto U, such that if we pull back the metric G on the manifold and we rescale it by R to the minus 2, then we're epsilon close to the cylindrical metric of scale 1, okay? In some large CK norm. Okay? So an epsilon neck is just a region in a Riemannian manifold that looks sufficiently close to a cylinder. And the image of the central of the two-sphere factor, the central two-sphere in this in the cylinder, I will denote this as a central two-sphere of the epsilon neck. Okay, so we may see some cylindrical region in a Riemannian manifold, and then in the middle there's going to be some two-sphere, and I'll call this a central two-sphere of the epsilon neck. Okay. Okay. So there are many central two-spheres because I can always deform them slightly, but if I see one, I call it a central two-sphere. And this one consists by the points of the central two spheres I will call centers. Okay, a center of an epsilon neck is just a point that's sufficiently far within this epsilon neck. Okay, so I'll need this piece of terminology, and then the other piece of terminology is kind of the Ricci flow version of this, and I'll call this a strong epsilon neck. So a strong epsilon neck is just the same definition as before, but now in the Ricci flow setting, and I'm going to require that the entire flow on a time interval of size r squared has to be close to the round shrinking cylinder here. Okay, so I've marked the changes here in red. So I want to be close to the cylinder on the time interval from -1 to 0, but on scale r. And so that means we're going to be close on the time interval from time t naught minus r squared to t naught. Okay, so this is just a little stronger statement. Okay, so let's just apply our new terminology, because this is some discussion that we'll need in the following. So let me consider the Bryan soliton. Recall this is a rotationally symmetric solution to the Ricci flow, where the warping function opens up like a square to the distance. And let me choose a point y, somewhere away from the tip of the Bryan soliton. And well, now if we look at a neighborhood of this point, and let's say we rescale the Bryan soliton to normalize the curvature at this point. Okay, so then we would normalize this corresponding two-sphere, the cross-sectional two-sphere. Okay, so the cross-sectional two-sphere has, if the distance to the base point is r, then the cross-sectional two-sphere is approximately of radius square root of r. So if we rescale by square root of r, then the distance to the center of the Bryan soliton is square root of r. So so as r goes to infinity, we're going to be very far away. Okay? And so this shows that if y is sufficiently far away from the center of rotation, then after rescaling, the neighborhood of y looks sufficiently close to a cylinder. Okay? So in other words, there's some constant c epsilon, such that if y has distance bigger than c epsilon from x bri, then yt is the center of an epsilon neck, or even the center of a strong epsilon neck, because we can also go backwards in time and it will always look very cylindrical. Okay, so this is a fact that we'll need quite often. So a Bryan soliton far away from the tip looks like a cylinder. And here's another lemma that we'll need, and I hope there's some intuition for this, which basically says that whenever we are in a Ricci flow, then in most cases, an epsilon neck, an epsilon prime neck is also a strong epsilon neck. Okay? So let me just state this more precisely. Let's assume we have a general Ricci flow. We take some point in this Ricci flow. Then there is, for any given epsilon, there's some smaller constant epsilon prime, such that if y is the center of only an epsilon prime neck, so only in its own time slice, and the flow satisfies the epsilon prime canonical neighborhood assumption below some scales, which just will make it possible to apply them near y and t, then y is also the center of a strong epsilon neck. Okay? So meaning we have control of the flow backwards in time. Okay? So how do you prove it? So basically, if at time t we're extremely close to a cylinder, then at earlier times we're somewhat close to a cylinder. Okay? And so how can we prove something like this? Well, we can prove this just by a limiting argument. So assume there's no such epsilon prime, let epsilon prime go to 0, find a sequence of counterexamples, and in the limit we would get a Ricci flow that's isometric to a cylinder at time t, but will maybe something different at earlier times, and that's just not possible. Okay? So it would be a kappa solution, and that's not possible. All right, so these are the two facts I'll need. So what I want to do next is I want to set up the toy case. So the proof of this uniqueness theorem is quite long. So it fills about, I don't know, 200 pages or something like this. And so there are a lot of technicalities and things we have to worry about. And just to understand the main ideas of the proof, I think it's better to consider one particular simplified setting. Right? And so I'm kind of going to try a setting. Okay, so let me now present to you the flow that I want to consider. So what I want to consider is basically a singular Ricci flow that starts from some singularity at time 0, and that strictly resolves the singularity as we go forward in time. You could even assume it's rotationally symmetric if you want to. Okay. So my thinking behind this is that, well, let's say we want to compare two singular Ricci flows with the same initial condition. Well, they're certainly going to be the same up until the first singular time, because up until the first singular time, they're just represented by conventional Ricci flows. So we certainly don't have any issues with uniqueness up until the first singular time. Okay. So the uniqueness problem arises when we pass the first singular time. And so that's why I'm saying, why don't we just start with some singular initial condition, right? Something that has these cylindrical cusps here. Okay, so let me now spell this out, what I mean by this. Okay, so the singular, so I want to start from a singularity, and I also don't want to have any accumulation of singular time. So I want the flow to be strictly smooth for positive times. Okay. So in other words, the flow restricted to the time interval from 0 to t is really represented by a non-singular, just conventional Ricci flow on some manifold M. Okay? And so this will simplify the presentation later as well, because I don't have to use the language of singular Ricci flows, at least for positive times. Okay? And I'll assume that this flow is kappa non-collapsed at scales below 1, and should satisfy, I should also say, satisfies the epsilon canonical neighborhood assumption. So let's just say for simplicity below scales 1, we can always rescale. And it's also assumed that the scalar curvature is always positive. This will also slightly simplify the presentation. Okay? Well, then the time 0 slice can be represented by some subset of the manifold M, and the metric on the time 0 slice is just the smooth limit as t goes to 0 of the metric. Okay, and this can be compactified by adding a single point here at the tip. All right, so this is what the flow should look like, and then I'm also going to look at these at this quantity of rho min, which is just the minimum of the curvature scale at time t. Okay, so essentially this is just the curvature scale at the tip, and so this measures approximately how singular the time slice is. Okay? Xt, let's say, is where the minimum is attained, and I'm going to assume, and this is maybe one of the strongest assumptions, just for simplicity, that rho min is weakly increasing. Okay, it's non-decreasing. Okay? So I don't want to somehow run into another singularity, and even worse, I just want to resolve the singularity. Okay? So rho min is of course 0 at time 0, and then I want to do strictly increase. Okay, so recall this condition has an interesting consequence. It implies that at the tip where the minimum is attained, that the scalar curvature, the time derivative of the scalar curvature, has to be non-positive. But recall, if we're at small curvature scales, we're going to be very close to a kappa solution. On a kappa solution, the opposite inequality is true. So that means these points have to be modeled on kappa solutions where time derivative of the scalar curvature is very close to 0. And this will imply that as we approach the singular time, the geometry near the tip will look like a Bryan soliton. Okay? So we can use this this rigidity discussion of Hamilton combined with Brendler's classification theorem. Okay, so this tip here will look very close to a Bryan soliton, and well, if we're far away from the tip, then we can't look close to a Bryan soliton. We can't look close to a sphere. So just by the canonical neighborhood assumption, the further away from the tip, we have to look close to a cylinder. Okay, so fourth, I will assume that for every point x and every time t, let's say of curvature scale less than 1, because by rescaling, we can always assume this is some of the threshold for the canonical neighborhood assumption. One of the following is true. Either x is a center of a strong epsilon x, so we're in a very cylindrical region here, or it is locally epsilon modeled on a Bryan soliton in such a way that somehow we were somehow close enough to the base, to the center of the Bryan soliton. Okay. And so this epsilon will be some universal epsilon, which I'll use for the entire proof, but I'll choose it smaller and smaller within the proof to just suit my purposes. Okay, so just to recall, we assume that essentially we want to just look at this part of the flow, which looks more or less rotationally symmetric, and it locally looks like, so each of these guys, they are basically covered by strong epsilon x, and in the end we see something that looks close to a Bryan soliton. All right, are there any questions on this setup? Oh. All right, so now I want to show uniqueness for these types of flows. So so how do we show uniqueness? Well, we show uniqueness by comparing two flows with the same initial condition. So let me take M and M prime, just as before, just as I've explained in this toy case. And let's suppose that they have isometric initial condition, and I want to show that the flows are the same, okay? So I assume that here times 0, these two cusps are the same, and I want to show that both flows are the same. Okay, so here's just one thought. If for some reason we could show that these flows had isometric time slices at some time t, some positive time t, well then after time t, the flow is just given by a smooth Ricci flow, just a non-singular Ricci flow. We definitely have uniqueness for those. So then this would imply that we would have that the flows past that time t, so for any times bigger or equal to t, that they would both be isometric, right? So the issue is really jumping from time 0 to some positive time. Okay? Once we have isometry for some other positive time, both flows have to remain the same. Okay? And so how are we going to do this? So roughly, and I'm going to make this more precise later, our strategy will be to construct what is called a comparison domain. So I try to draw this in red here, which is some kind of subset of spacetime that stays away from the somehow singular points or from the points of high curvature. And we also want to construct a map phi into M prime that is 1 plus eta by Lipschitz for some small eta. Okay? And so this will tell us that this part of the singular Ricci flow will be very close to this part. Okay? And then what we will do is we'll let eta go to 0 and we'll let n go to m. So at some point, m will have isometry between both flows. And so this is approximately our strategy, and I'll tell you more precisely later. Okay, so let me pause with this discussion, or this space-time discussion. I'll get back to the toy case, but I think now we have to do some real analysis. And in order to start this, let me first discuss how can we actually show uniqueness of the Ricci flow in the most basic case, meaning the non-singular case. I mean, there's certainly going to be some techniques that we have to take over from this case. Okay, so let me prove the uniqueness for Ricci flows for conventional Ricci flows. Okay, so again, I'm going to phrase it a little bit in the language that we'll need later. Okay, so let me assume I have two Ricci flows, and let's assume their initial conditions are isometric. And then I want to show that both flows are isometric. Okay? So how do we show this? And so this is the standard proof. I'm just writing this maybe in a slightly different language. Okay? So first of all, I'm going to choose an isometry between the two initial time slices. And I'll call this a comparison map, right? But it's just an isometry between m at time 0 and m prime at time 0. And then I'm going to choose an h, which I call a perturbation. And it's just the pullback of g prime via phi minus g. Okay? And so h basically measures how good of an isometry phi is at later times. Okay? So at time 0, phi is an isometry, so h is equal to 0. But then later, h might get bigger. So now we could say, well, is there some nice evolution equation of h? Maybe we can show that h remains small or is equal, or it has to be 0 for later times. And the problem is that h does not satisfy a strong parabolic equation. Right? It only satisfies some weak parabolic equation. And here is where this de Turck's trick comes in. Right? In de Turck's trick, we say, well, let's not look at a static phi. What we should do instead is we should move phi by a nice equation and then see what equation h satisfies. Okay? And so what we're going to do here is we're going to move phi inverse, so the inverse of the map phi from m prime to m by harmonic map heat flow. Okay? So harmonic map heat flow is just the heat equation for maps. Okay? So remember, so if you you can always define the heat equation, and you have a Laplacian on this side, and the Laplacian is just the second derivative of a function if we walk along geodesics that somehow form whose velocity vectors form an orthonormal frame. Okay? And so now instead of taking second derivatives, what we'll have to do is we'll have to look at we have to walk along a curve passing through a point. We have to look at its image curve, and we have to look at the geodesic curvature of this image. Okay, so this will replace the second derivative if we map into a manifold and not into a vector space. Okay, so, but the harmonic map heat flow can be defined. This is a strongly parabolic equation, so that's no problem. At least define phi for some small times. And now if phi moves by harmonic map heat flow, the nice thing is that the evolution equation for h, which lives on m, satisfies this nice nonlinear parabolic equation. Right? And this is often called the Ricci de Turck flow. Okay, so we have this Laplacian of h here. We have a 0th order linear term here, and then we have some quadratic terms. And now we can just apply standard parabolic theory, and we'll get that. Well, we have uniqueness of solutions of this equation, and well, since h at time 0 is 0, h has to be 0 everywhere. Okay? So that means phi has to remain in isometry. And then we inspect this equation again, and we see that actually phi didn't move at all. Okay, so this is the proof that we want to use. So we somehow evolve the comparison map by harmonic map heat flow. Okay, so just to foreshadow here a bit, what we're going to do later is we're going to look at h and phi. We're always going to evolve phi by the harmonic map heat flow, but what will happen very often is that we can't apply this last step. So we won't be able to say that h is strictly equal to 0 somewhere. Instead, we will only be able to say that h remains very small, and then we can let this eta go to 0 later. Okay? And in a domain where h is very small, this quadratic term will go away, and we're left with these the linear part. Can be neglected, I should say, and we're going to be left with this linear part. Okay? On this linear part, this linear equation here is called the linearized Ricci de Turck flow. Okay? So this is just the Laplacian, the connection Laplacian, and Rm applied to h is just somehow the obvious contraction of the curvature tensor with a symmetric 0-2 tensor. Okay, so the idea will be in the following: to first look at this linearized Ricci de Turck flow, understand this more precisely, then make statements on the nonlinear Ricci de Turck flow, and then use this to make statements on comparisons of two different Ricci flows. Okay? And so with this being said, let me move to the local stability analysis. Okay? So this will be maybe a bit more complicated, but I'll try to run through this slowly. Okay, so again, what I want to do in the following is I want to first prove some theorems on the linearized Ricci-Deterk flow. Okay, so here's the setup that I want to consider. Let me just consider a standard Ricci flow on a three-dimensional manifold. And for simplicity, let's just assume that the scalar curvature is everywhere positive. Okay? We can just, it's not so hard to generalize this for to a more general setting. And then I'm going to look at a linearized Ricci-Deterk flow on that Ricci flow as a background. Okay, so this is the linearized Ricci-Deterk flow. I just throw away the nonlinear part, and I consider the linear equation. And so here's somehow the key estimate that we're going to be using. And so this is an estimate that was derived in a paper by Anderson and Chow in 2005. So in this paper, Anderson and Chow derive an evolution equation for assuming you have a linearized Ricci-Deterk flow, they derive an evolution equation for the norm of H divided by the scalar curvature. Okay? And so they get this equation. So they get some Laplacian term and then some gradient term. Right? And so what we can do here is we can really just, so the nice thing here is we can apply the maximum principle to this quantity, and we get that this quantity has to be non-increasing in T. So that's why this is kind of a cool estimate. So how to prove this? Well, essentially this is just a computation, but let me just give you some more details. Let me just call a box, let me call this the heat operator. And then I'm going to apply the heat operator to H divided by R. So now there's a formula for the heat operator applied to a quotient. It's just this formula. And now I'm going to apply the heat operator to the norm of H. This is just going to be bounded by 2 times RMH comma H divided by H. And the heat operator applied to the scalar curvature is 2 times Ricci squared. Okay? And so now, what I now need to show is that this term here is non-positive. And then I'm done. And this reduces to this inequality between tensors. Okay? And so this can be reduced to a simple inequality involving 6 unknowns. Okay, it's a little difficult to prove this, but it can be done, and we can prove this. All right. So this is some of the key estimate. This is a nice computation, and Ben Chow showed me this computation once, or this result, and showed me, is there something that we can get out of this? And so if you look at this, so when I saw this result first, stating that this maximum is non-increasing, I somehow had, my first reaction was that this seems like a not very good estimate. Right? And I first saw the disadvantages of this estimate. So what does this estimate say? Well, it says basically that if we look at, so H basically stands for some, a variation of a Ricci flow, for some perturbation of a Ricci flow. It's some difference, and it measures. So what we're basically saying is that differences between Ricci flows don't increase if we weigh them by the inverse of the scalar curvature. Okay? And so the way I saw this first was that, well, this seems like, not a very helpful estimate, because it just says that if we're starting with some H, which is maybe not very big, medium sized, whenever R is somehow approximately 1, then maybe at a later time, H may become very large, but R may also become very large. And so it's somehow not very exciting to know that the quotient is not increasing, okay? So differences at macroscopic scales may have big effects at microscopic scales. And so some of the standard example, which is also the equality case essentially in this theorem, is just where we take a round sphere which contracts to a point, okay? So let me take G to be the standard round sphere contracting to a point, and let me take G prime to be a slightly smaller sphere. So then if we take the difference measured with respect to the metric GT, then this difference scales like some number divided by 1 minus 4t. So this goes to infinity at the singular time, which kind of makes sense, because if we're making the sphere a little smaller, then the singularity occurs a little earlier somehow. So we should expect that somehow the difference between these two metrics should be enormous at this time. And this is comparable to the scalar curvature, and all this estimate is saying that, well, if we divide by the scalar curvature, this term is non-increasing. But now we can also, but on the other hand, so the positive thing of this estimate is that we can turn this sentence around. Namely that this estimate tells us that differences at microscopic scales have little effect on macroscopic scales. And so this is exactly the type of examples that we're going to be looking at. So we are worried that there's some discrepancy between two solutions to the Ricci flow that are somehow localized in a region where R is very big. So let's say this discrepancy is measured by H, and this discrepancy is let's say on the order of 1 in a region where R is very large. Then this quotient has to be very small. And now the result of Anderson Chows is that the maximum of this quotient has to be non-increasing. So that means at a later time, this quotient has to remain very small. But now the scalar curvature is approximately 1. And so this will imply that H is very small. So this is exactly the direction that we need for showing uniqueness here. Okay, so how do we achieve this? Sorry, maybe I should ask, are there any questions? Okay, so now, okay, so this is more like the philosophy behind this. So maybe showing us that we're on the right track. So how do we actually prove this? So first of all, let me again focus on the linearized Ricci-Deterk flow. And it turns out what's going to be very useful is to prove what I call a vanishing theorem on kappa solutions. So here's the vanishing theorem. It's a quite quick statement. So let me consider a kappa solution. Recall that's a cylinder, a brine soliton, sphere, or Perelman's ellipsoid. And let me consider a linearized Ricci-Deterk flow on this kappa solution, which exists for all non-positive times. And let me assume that this flow satisfies the following bound, that the norm of H is bounded by some constant times some power of the scalar curvature that's slightly bigger than 1 or bigger than 1. Okay. Then the statement is that H has to vanish everywhere. Okay. So there are no such non-trivial linearized Ricci-Deterk flows. Okay. So you'll see later why this is somehow going to be important for our purposes. But so what I want to do in the following is I want to prove this this vanishing theorem. Okay, so the proof is relatively nice. Okay, so here's the proof. So first of all, recall that on a kappa solution, the scalar curvature is always going to be uniformly bounded. So a bound on an upper bound of this form can always be replaced by just upper bound of the form C times C prime times R. Okay? So the scalar curvature is bounded from above by a multiple of R as well. And now let me look at the quotient of H divided by R. Okay? And I'm going to assume that H is non-zero. So that means I can find a sequence of points xi, ti, such that this quotient converges to the supremum of the quotient over the entire kappa solution. Okay? Just choose a sequence of points xi and ti so that we have this convergence. All right, so what can we say about the scalar curvature at these points? Well, I just do the simple computation. The scalar curvature to the gamma at these points is equal to R to the 1 plus gamma divided by R. Now I just plug in this bound, the reverse direction of this bound, or of this bound. I can bound this guy by H, and then I have some quotient of H divided by R, and well, this converges to C naught, which was positive. Okay, so I get that the scalar curvature at these points, xi, ti, will not converge to 0. Okay, it will stay bounded away from 0. Okay, so what does this mean geometrically? So let's assume we're on on a round shrinking cylinder. Well, in a round shrinking cylinder, this means that the times ti cannot go to minus infinity, because if we go to minus infinity, the scalar curvature would go to 0. Or if we were on a Bryan soliton, then the points xi cannot go to infinity, because this, on the Bryan soliton, the scalar curvature goes to 0 at spatial infinity. All right, and so what we can do now is we can just pass to a subsequent. After we can now take a geometric limit. Right? So what I'm going to do is I'm going to look at the Ricci flow time shifted by ti. I'm not going to rescale it. I don't need to. Based at the points xi's, and after passing to a subsequence, these Ricci flows will converge to some limiting ancient Ricci flow. Okay. So again, let's assume we are on a round shrinking cylinder. Then we know that the times ti cannot go to minus infinity. The points xi can lie anywhere, but the cylinder is homogeneous. So what I will get in the limit is just some cylinder, maybe slightly rescaled. If I'm on the Bryan soliton, then the points xi cannot run out to spatial infinity, so they have to remain close to the tip of the Bryan soliton. So the limit is going to be a Bryan soliton again. Slightly more interesting is the case where we have this ellipsoid of Perelman. In this case, we have to stay close to the tips of this ellipsoid, and then we may converge to a Bryan soliton, because we may see this ellipsoid stretch and converge to a Bryan soliton. But we can always take a limit. So we have so either we can use some compactness theory for kappa solutions, or we can just take the limit by knowing what they are. Okay, so we converge to some limiting solution, which is again a kappa solution. And then, well, we can use the fact that H is bounded by the scalar curvature to pass to another subsequence to let the linearized Ricci flow converge to some solution to the linearized Ricci flow in the limit. Okay, so now we have the same situation as before. We have a kappa solution and a solution to the linearized Ricci flow. And again, we have the same inequality. This just passes to the limit. And we have this inequality as before. And the only difference here is that now we have equality in this inequality at the base point, okay? Because that's how we've chosen our points xi, ti. Okay? So now we have equality at the base point x infinity, okay? because we've chosen xi so that this quotient converges to the suprema. Okay, so let me slide this box up to the top. Also, what we can now do is we can just apply the Anderson-Chow estimate and the strong maximum principle to this inequality. And we get immediately that, that the left-hand side has to be constant. Okay? Remember, this is non-increasing under the flow, but if we attain the maximum at the final time, then just by the strong maximum principle, we have to have, this quantity has to be constant everywhere. Okay. Okay, now let's plug this back into the previous equation. Again, I'm going to do the same computations before. But now I know that this quotient here is constant. So I get that the scalar curvature has to be uniformly bounded away from 0 on the entire kappa solution. But this is false on a kappa solution. On a Bryan soliton, the scalar curvature goes to 0 at spatial infinity. On the cylinder, the scalar curvature goes to 0, as time goes to minus infinity and so on. Okay, so now this proves this theorem. Are there any questions? All right, so this is somehow kind of will turn out to be a useful theorem for linearized Ricci de Turk flow. But ultimately, we're concerned with nonlinear Ricci de Turk flow. So how can we use this linear theory to get some nonlinear result? Okay. And so just to introduce this, let me just highlight this principle, how we can get from the linear equation to a nonlinear equation. So this is more philosophical. Again, so let's assume we have a Ricci flow background, and we have a solution now to the nonlinear Ricci de Turk flow equation. Okay? So I'm going to now use the following observation. Let me take some constant a, much smaller than 1. And let me assume that h is maybe very small, so that if I divide h by a, this is going to be reasonably sized. Okay? So maybe the norm of h is approximately a or something like this. And so what I can do is I can divide this equation on both sides by a. Okay? So I put a divided by a everywhere. But now here are these quadratic terms. So if I put an h divided by a everywhere, I get an extra a factor here. Yeah? And so now the observation is that maybe if for some reasons we're allowed to take ai going to 0 in such a way that a, and we look at somehow a sequence of solutions to nonlinear Ricci de Turk flow, such that hi divided by ai converges to some h infinity, okay? Well, then we can take, and then assuming we have good enough derivative bounds, which we should have in a parabolic setting, then this equation passes to the limit, and these quadratic terms go away, and we end up with a linearized Ricci de Turk flow. Okay, so basically this is what we want to do. We want to take a sequence of nonlinear Ricci de Turk flows. We want to divide them by where hi goes to 0. We want to divide them by small numbers, and in the limit we should get some linearized Ricci de Turk flow. Okay, sorry for this guy here. Okay, so now let me apply this, and let me actually derive a useful theorem. Okay? So in the following, I'm going to consider a kappa non-collapsed Ricci flow, and I'm going to assume that I have the epsilon canonical neighborhood assumption below scale 1. So basically, I want to be in the setup as in the toy case, a 3-dimensional Ricci flow, of course. And I'm going to consider a nonlinear solution to the Ricci de Turk flow, H. Okay? And my goal will now be to control this solution H as I move forward in time in a certain way. I want to somehow say if H at earlier times is small, then later it has to be small, or it has to decay, or things like that. I want to make a statement like this. And in order to do this, I'm going to form the following quantity. I'm going to take the norm of H, and I'm going to divide this by the scalar curvature to some power that's bigger than 1. E has to be bigger than 1. I'll fix E later, but for now, E is just some number bigger than 1. And I'm also going to multiply this by e to the minus ht, where h is a constant that I'll choose later as well. Okay, so now this quantity more or less can be used to control h, right? Modulo these two weights here. And now I can finally state the main theorem for nonlinear Ricci de Turk flows, which I'll refer to often as a semi-local maximum principle, or an interior decay estimate. Okay? So it says the following: for any alpha will show up later, kappa, which is just in this definition here, and any e, there are constants, well, h, epsilon, eta, and l, such that the following is true. If I take a parabolic neighborhood around some point x at time t of size L times the curvature scale at x. Okay? So I'm going to call this P. And if on this parabolic neighborhood, H is sufficiently small pointwise, H should be bounded by eta. Okay? Eta is basically some kind of threshold, and will later be some kind of threshold below which we can approximate H by a linearized Ricci de Turk flow. Then we have the following bound. Then we get that Q at the point X, so at this interior point, is bounded from above by alpha times the supremum of Q over the entire parabolic neighborhood. Okay, so recall alpha could be chosen as small as we want, but then we may have to choose L larger, or eta larger, or H larger. Okay, so maybe I should say, why do I call this a semi-local maximum principle? So let me, for example, choose alpha to be 1/2, right? So then this estimate says that Q cannot attain a maximum at x, okay? Because if it attained a maximum at x over this parabolic neighborhood, this bound would be violated, okay? So it gives us some kind of statement like a maximum principle, but it's not kind of like it's not a local statement like in a maximum principle or a pointwise statement. We really have to consider the entire parabolic neighborhood, and we need to make sure that that H is defined on this parabolic neighborhood, and that it's also sufficiently small so that we can make this approximation. Right? On the other hand, we get something that's slightly better than a maximum principle. We can really choose alpha as small as we want. So we really get some interior decay. So if you're really far away from any boundary, we really know that Q is very, very small at X compared to its surroundings. Okay, so now let me prove this semi-local maximum principle. And so the proof is essentially, you'll see, is essentially an application of the vanishing theorem. But we'll have to be careful to do this. Okay? Okay, so now let me fix alpha, kappa, and E and argue by contradiction. Okay? So that means I cannot find any of these constants so that the statement is correct. Okay? Okay? So that means I can choose, so let me now choose hi and li going to infinity and eta I and epsilon I going to 0. And for each I should be able to come up with some counterexample to the statement. Okay, so that means hi is bounded by eta I, so hi goes to 0. And if I said, let me just set ri to be the curvature scale at xi ti, then the opposite of this bound holds. Okay? So this is the opposite of this bound. I've just reversed the left-hand side and the right-hand side. And so what does this mean? Well, on pi, the supremum is just, bounds this quantity here. And if I evaluate it at xi, it's just this quantity. Okay? And now what I'm going to do is I'm just going to divide by hi at xi ti and I guess multiply by r to the e. Okay, so on this parabolic neighborhood pi, this bound is true. So if I normalize hi by hi at the point xi ti, then this is bounded by alpha to the -1 times this exponential factor. So I think I've added these two together here. Times the quotient of the scalar curvature at any point divided by the scalar curvature at the base point to the power of e. Okay, so the interesting thing is that the opposite of this inequality is actually a uniform bound on hi over the parabolic neighborhood, or some pointwise bound on hi over the parabolic neighborhood. Okay, so now, so let's assume this is true for any I. So now let me pass to a subsequence. Recall Ri is the curvature scale at rho xi ti. Sorry, let me take a geometric limit of the rescaled flow. So I'm going to rescale the flow so that Ri corresponds to 1. So the curvature scale at xi ti is 1. And I'm skipping some details here, but most of the time I can pass this flow to a limit. Okay? So now I obtain this limiting flow. Sorry, this may not be defined on this type of time interval, but I'm just obtain some limiting flow. And then, well, hi divided by the norm of hi at the base point, well, the norm of this is bounded by the quotient of these scalar curvatures. Okay? So this is locally uniformly bounded because we've normalized this guy to be 1. And this, just by the convergence here, this guy will converge to the scalar curvature at m infinity. Okay. All right, so we're going to converge to some flow. And well, hi at the base point, at least, or anywhere actually, converges, we know converges to 0. Okay? So we're dividing hi here by a number that goes to 0. And so therefore, in the limit, we obtain a solution to the linearized Ricci de Turck flow. Okay, so now we have, so what do we have? So we have some Ricci flow in the limit, a linearized solution to the Ricci de Turck flow in the limit. And so let's analyze what properties this flow has. First of all, well, at the base point, just by way of normalizing, at the base point, this h infinity has to be equal to 1, and the curvature scale also has to be equal to 1, okay? Because we've rescaled and normalized in this way. And then let's look at this equation and pass this equation to the limit. Okay? So essentially, we're getting that h infinity is bounded from above by I don't know why I've chosen it. I think there's some 10 for some. Sorry, I forgot why I chose a 10 here. But oh, sorry. So this RXITI converges to 1, or maybe it's 1/3 or something like this. So because so this converges to 1, or some some number that we can write down, and so on the right hand side we really see the limit of some constant times alpha to the -1. Well, we've applied a time shift, so the ti goes away. So we just have this exponential term where we rescale by ri squared. So we have to multiply by ri squared here. And then we get the scalar curvature in the limit. Okay. All right, so we have this bound in the limit. And now there are two cases. So first of all, there's the case when the lim_inf of ri is positive, meaning that ri did not converge to 0. Okay? So we looked at, basically we took a limit at macroscopic scales. Okay? And in this case, well, ri squared goes to, stays bounded away from 0, but hi goes to infinity. Okay? So this term, at least for negative times, goes to 0. And so then this equation implies that h infinity has to be equal to 0 for negative times. But then just by continuity, h infinity has to be equal to 0 everywhere, contradicting this choice. The other case, maybe the more interesting case, is where the lim_inf of ri is equal to 0. So in this case, at some point, we're going below the canonical neighborhood scale. And this will imply that the limit is a kappa solution. Okay. So now the limit is a kappa solution. Let's just discard this term. And what we'll get in the limit is that h is bounded from above by the scalar curvature to some power e. And so now we can just apply the vanishing theorem, and we get that h infinity, it has to vanish everywhere, which again contradicts with this fact. Okay. And so this finishes the proof. So I hope this was not too technical. Are there any questions? Okay, so let me just recap. All we need is the statement for the remainder. So what we've proven is that as long as h is small enough, smaller than some threshold, we can make a statement on this quantity q, which essentially controls h. So q in the interior of some large enough parabolic neighborhood is bounded from above by its supremum. Okay, so yeah, so we're going to come back to the semi-local maximum principle, but let me just take this to the test and show you briefly why this is going to be useful. Okay, so I'm just going to show you a few consequences of the semi-local maximum principle. And I'm going to apply some minor generalizations of this principle, but just to give you the flavor of what we can achieve with this. So let's assume we just take some Ricci flow as above here. And let's assume for some reason we know that h at time 0 is very small. Okay? So let's assume, assume this will imply that q, and we're going to express the smallness of h in terms of q, and we're going to say that q at time 0 is bounded from above by some bound q bar, and let me divide this by h to the -1. Okay, so I just want some small number here, and I have some h which is assumed to be large anyway, so I'm just reusing this here. Okay. And let me assume that h is everywhere bounded from above by eta on the entire flow. So then the semi-local maximum principle will imply that q is bounded from above by q bar everywhere. Okay? So why is that true? Well, assume that q would become bigger than q bar at some point. Just look at the maximum point of q. Well, by the semi-local maximum principle, this maximum point of q cannot somehow cannot occur unless the parabolic neighborhood does not exist. So unless we're somehow too close to the initial time. Okay? And if the parabolic neighborhood intersects the initial time, there's some other version of the semi-local maximum principle, where we can use this bound as well. Or let me say it in a different way. We get some bound on Q for some time due to this increased bound, somehow this improved bound involving the H. And then for later times, Q can never attain a maximum anymore compared to all the previous time slices by the semi-local maximum principle. So a bound of the form Q is bounded by Q bar is being preserved if we move forward in time. But this is, of course, only true as long as H is bounded by eta. And remember, we often just want to control H. And we don't want to have a condition of the form H is bounded by eta in a statement like this. And so what we'll do in the following, what we'll do quite often is that we'll assume that we'll only look at bounds of the form Q is less than Q bar in such a way that Q bar is chosen in such a way that it implies that H is bounded by eta. Okay? So if that's the case, we can drop this assumption, and we can prove as before that we can maintain a bound Q is bounded by Q bar over the entire flow, because this will automatically imply that H is bounded by eta. And then I also should say that the statement here, there's a more general statement, right? Somehow the dependence of the constants can be made much more precise, and in particular, for example, we can make eta independent of alpha and kappa, and we can also make H independent of alpha and kappa. So we can often just choose alpha very small, and the only change that occurs here is that L has to be chosen very large. All right, so yeah, so we'll get back to this principle, and I hope this will make more sense later if this was too confusing. Are there any questions so far? Okay, so I'm running maybe a slightly ahead of schedule, but what I just want to do in the last 10 minutes is start a little bit with the third lecture and talk a little bit about the construction of the comparison map. Okay, so this okay, so again, so the lecture will be this third lecture will, which I'm officially starting tomorrow, will conclude the proof of the uniqueness theorem. So what we'll discuss first is we'll construct a comparison map between two singular Ricci flows, and I'll explain how this is performed. Then there will be a cap extension problem, which we'll discuss later what the problem is and how we resolve it. Then I'll also discuss some of the general case, the one that goes beyond the toy case. And then I'll somehow discuss some of the precise statements of the main results in more detail and indicate more further byproducts of the proof, and make this continuous dependence more concrete. All right, so let me just start with this first chapter, and I just to give us some first ideas here. Okay, let me just recap first. What we're going to consider here is really this toy case. Okay, so we consider singular Ricci flows that start from this singular initial metric and that immediately resolve this this cusp here. And the important property that we may need to focus on in the following is this property, okay? So which says that whenever we take a point of curvature scale less than 1, then we can somehow consider this as some kind of almost singular scale, and we make the assumption that that any such point is either the center of a strong epsilon neck or it's locally epsilon modeled on a kappa solution. Okay? All right, so we're only going to worry about flows of this type. And then, as I said, what will be our strategy? So again, our strategy will be to take two of these flows, M and M prime, with isometric initial condition, and our goal will be to compare both flows and show that they are the same, or isometric. And so we'll do this by constructing this comparison map. So we'll highlight a comparison, we'll define a comparison domain N, and then we'll define a map phi from N into M prime that is 1 plus eta bielliptids for some small eta. For some small eta. So And so what we've learned from the non-singular case was that it seems to make sense that the inverse of phi should evolve by harmonic map heat flow. Right? So this is maybe what I'm going to add to the strategy here. We want to make sure that phi evolves by evolves by harmonic map heat flow. So we can write down the equation still locally, and we want that equation to be true. And then again, our goal will be to let eta go to 0 and n go to m. And in the limit, we want to obtain an isometry between m and m prime. Okay. And so maybe what we've learned from the previous few chapters is that maybe a good way of controlling phi, or some of the closeness of m and m prime, is to look at this perturbation h, right? So we're going to look at the pullback of g prime onto n, and we're going to take the difference with g. Okay? So if h is small, then this would, if h is 0, then this would mean that phi is an isometry of Ricci flow spacetimes, or local isometry. And if h is small, then this would establish some bi-Lipschitz condition. And the good thing about h is that it evolves by the nonlinear Ricci de Turck flow, and that we can control h via the semi-local maximum principle. Well, at least as long as we're far enough away from the boundary of this parabolic domain, because recall in the semi-local maximum principle, we had to look at these larger parabolic neighborhoods. We just need to make sure that h is defined everywhere on these parabolic neighborhoods, right? So whenever we see a point that's somehow sufficiently far away from the boundary of n, and when we can fit a parabolic neighborhood into this red domain n, then we can apply this semi-local maximum principle, which tells us something about the size of h at this point. Okay, all right. Okay, so essentially there are two different tasks. So we have to first construct this comparison domain n, and n will be constructed in such a way that we're staying away from singularities, or away from regions where the curvature is too high. And then we have to construct phi. Okay? So our first goal will be to construct the comparison domain. Okay? And so in order to do this, let me now state a lemma that will characterize what this comparison domain should look like. And what I'm going to do here is I'm first going to state the lemma, and it may be confusing at first, but then I'm going to show you a picture, and I think it should show pretty clearly what this comparison domain, what I mean by the lemma. Okay, so please stay with me for this slide, and I'm going to review this again in the next class anyway. So, okay, so what I'm going to do in the following is I'm going to fix some constant delta n, which will be some kind of precision of strong delta n neck. And I'm also going to choose some scale lambda, which will depend on delta n. I'll determine those later. And then I'm going to choose a scale, which I'll call R-comp. And R-comp will be the comparison scale. I'll call this a comparison scale. Then based on R-comp, I'm going to choose a sequence of times that are spaced R-comp squared away from one another. Okay? I'm starting at 0, R-comp squared, 2 times R-comp squared, and so on. And I'm going to do this up until I reach some macroscopic time t. Maybe t is some of the final time of the flow. Let's say the flow is defined at time capital T. So later I may choose R-comp smaller and smaller, and that will cause j to go to infinity, of course. Maybe I will always want to keep t fixed. And then I will choose some j naught in the subset, minimal, such that this inequality is satisfied. So I want to choose the first j naught such that rho min at time tj naught is bigger than lambda times R-comp. Okay? The first time, somehow the solution is somehow not so singular anymore. Okay, so with these objects, I will now define what this comparison domain. And this comparison domain n will be a subset of the singular Ricci flow m, and it will have this form. So it will be a union of certain time slabs, n1 and so on until nj, such that the following is true. So every nj is just a product of some subset nj of m times this time interval from time tj minus 1 to time tj. And these nj's, they're decreasing subsets up until the j naught. Then I'm going to, so then this nj is, it's just some product domain defined from time tj to time tj minus 1 to some time tj. And in the final time slice, I want the boundary of nj to be a central two-sphere of a strong delta neck at scale r-com. And then furthermore, I want the scalar, so basically this curvature scale to be bigger than 1/2 times r-com on the union of the first j naught many comparison time slabs. And then lastly, for any j that's bigger than j naught, I just want nj to be the entire manifold times the corresponding time interval. Okay, so this is maybe a lot of statements, but let me just draw a picture here, and then I'll finish, and in the next class I'll review this again so that we all have the clear picture. Okay, so here I've drawn a singular Ricci flow starting from this cusp manifold, and I want to construct a comparison domain. I'm going to mark this in red. So what I'm going to do is, and this comparison domain should consist of product neighborhoods. Okay, so this should, what I try to draw here is some set of m cross the time interval from t naught to t1. Okay? And then the next n2 should look like this, should be some other product neighborhood. And it should just be a little smaller. And then I take another product neighborhood and so on, up until that last time tj naught, or tj naught minus 1. Okay. Okay. So just to recap the conditions here, every n1, n2, n3, and so on is a product domain. These product domains get smaller and smaller. Then I want the boundary here always at the final time of each product domain. I want the boundary to be a central two-sphere of a delta n neck. Okay, so I want this to look sufficiently cylindrical near the boundary here, and the scale of this delta neck should be r-comp. So roughly rho should be equal to r-comp near the boundary here, and this will imply that rho is roughly equal to 2 times r-comp here. Right? So it basically goes from 2 times r-comp to r-comp. Then we're going back until this curvature scale is, or the size of the cross-sectional two-sphere is 2 times r-comp. Then we go to up r-comp and so on. And we're going up by r-comp squared in time every single time. And then I do this up until time tj naught. And this is the last time where rho min is less than 10, I don't know why I have a 10 here, sorry, where it is less than lambda times r-comp. And then for any further time, so this is the last time. And then for any further time, I'm just going to choose the entire flow here. Okay. So this is going to be my comparison domain. And so what I'm going to do in the next class is I'm going to explain why such a comparison domain with the desired properties exists, and then how we construct a comparison map from this comparison domain. Okay. And then again, I'm going to review this construction and the properties again. All right, so I'm going to stop here. Thanks for your attention, and I'll hope to see you again tomorrow.
Thank you, Richard. Are there any questions? I don't see any questions. So thank you again for this very nice lecture, and we'll see each other tomorrow, same time, same place.
Okay, great. Thanks. Yeah, see you tomorrow.
Nice. Have a nice day.
Yeah. Have a nice evening. Bye.
C'est lui qui arrive en fait.